Hello, everyone. My name is Massi, and I'm the CEO of Metabob.
And I'm Avi, the CTO.
Now, Metabob is a generative AI tool that helps developers cut debugging time in half. As a conference full of developers, we all know how challenging and time-consuming is debugging, which is by far the most time-consuming and challenging aspect of every software developer day-to-day. In fact, engineers spend more than half of their day looking for bugs, which costs companies an astonishing average of $160 per hour per developer. And currently, only about 10% of critical bugs can actually be caught by current static analysis tool in the market. Now, I'm sure you all might think, why can't I use ChatGPT or Copilot for it? Well, despite 60% of newly developed code is being written with Copilot, in 40% of cases, actually code generated by Copilot contain logical bugs and security vulnerabilities. And the main reason why is because LLMs have challenges to properly construct context within the code, and they're extremely sensitive based on user prompt. However, like for the past 10 years, alternatively, developers have been using rule-based static analysis tool. You might be familiar with Sonar, Covariety, and many more to detect problem. Even though those are heavily relying on the developer ability to define problem through rules, and they can only detect the rules local to a line of code. So they're mainly used for detecting problems such as syntax and style. And they also generate a lot of noise. Here comes Metabob. Our AI static analysis tool is uniquely able to detect and fix critical and logical bugs within the code that nobody else can find. And how it works is very simple. Avi, in a couple of minutes, will go through the more technical explanation. But initially, we develop a graph attention neural network. That's really the core of our IP. So we didn't start with LLMs like most other companies. And then our GNN initially analyzed the code base with no limitations in the number of code and characters. After we do that, the detected problem and contextual information are then stored and sent to our own LLM. And lastly, our LLM generate a problem explanations, and we also provide code recommendations to resolve the problems we detect. Now, how we train the model is we started with mainly open source data. So we use GitHub open source, but over time, we've also added company SOP. We use Reddit, Stack Overflow, and many more data sets. Happy to explain more during the Q&A sessions. Now,
yeah, and the core value of using a technique like ours as opposed to using an LLM-first technique is that we're able to minimize the amount of context hallucination that can be generated by the LLM itself by being able to isolate specific regions and predict why those regions are needing either refactoring or improvements or other changes to the program logic in order to resolve critical vulnerabilities. And that allows us to then provide additional metadata to those LLMs, provide very structured and specific fixes that directly resolve that problem that we've detected, as well as provide additional context information about why it's occurring and broader changes you can do to the design of the program to fix it in other places as well.
So our tool, first of all, we are available on VS Code, so all of you can try for free. It's IDE extensions. You can also find us on GitHub. And we also have an on-prem solutions targeting enterprises. We have 3 core use cases right now that we sell the tool for. So first and foremost, for maintaining legacy code. As we all know, legacy code is usually outdated, extremely long, and developers, especially when newly hired, they don't really know what to do with it. Like any change they make, they might break the entire code. And our tool is uniquely able to help companies retain institutional knowledge and tell developers what each change will, what will be the consequence of each change they will make. We also help, obviously, to detect new issues or to detect issues in newly written code. So as developers write code, we always point out the area of the code that can be improved or fixed. And lastly, a lot of engineers are currently using us along with Copilot or other generative AI solutions, as our tool is uniquely able to validate the cohesiveness of AI and improve the quality of code generations. We've done many case studies in the past few years since we launched the tool. Most recently, we published one where it shows that we have 50% of higher detection rate of critical issues compared to standard rule-based static analysis tool. We also have helped company to save 36% on manual code review and refactoring tasks. And we found, just for that company, over 3,000 critical issues. Since we launched just this year, we started to monetize and sell to enterprise. We already have several Fortune 500 companies, and we are one of the fastest tool on VS Code in terms of growth. I think we are close to 50,000 active users there. And when it comes to our tech, well, I'll let our CTO talk about it a bit more.
Yeah, so let's get into a little bit more about exactly what makes us unique and how our overall methodology functions. As Massi mentioned earlier, one of our core IPs is the graph neural network that we developed to be able to detect problems within source code. However, what we've really developed is an overall methodology to be able to take the very unstructured and non-standardized raw data and produce meaningful insights that we can then use to apply to new code bases, new pieces of code, alongside other AI techniques. And that really starts with understanding what the original source data is. And for us, it's mainly pull requests or other change comments and commit messages from either open source code bases or, more importantly for most enterprises, their own company review history. Using that information, we built a methodology that allows us to standardize all of these into very specific markers that can detect certain components, do RCA to determine exactly what needed to be changed and why, depending on exactly how well written these PRs are. And then from there, we're able to take those insights and extract all of the most relevant changes that have been made to each part of the code base and understand how they fit within context. Using that information, we're then able to use our graph neural network model to be able to predict essentially which locations within the code base are most likely to need to be changed in that current iteration in order to resolve certain issues that may be detected. And by doing that, we're able to then isolate specific regions of the code based off their semantic, logical, and structural components. Essentially, we're taking the code property graph and then simplifying it using a set of ML techniques to allow us to be able to detect logical groupings that allow us to then perform our overall inferencing with the graph neural network at runtime, which is something that's typically much more difficult to do. And then from there, what we're able to do is extract the adjacent information as well from the code base, essentially from the docs or the inline comments or the other semantic markers that are present. And by refining all of those together along with our detection categories and the metadata about those detections that we are able to extract from the original source PRs, we're then able to provide a very structured set of context to an LLM to then do code explanations about the problem, which can provide a much more human-readable front end that a regular developer could understand regardless of their level of seniority or their familiarity with the code base. In addition, we're able to use that same information to provide very structured fixes with similar examples from other generic code bases, as well as the similar structures that have been used for other changes within that same code base history. So this is the end of the backend portion of it. So from the user standpoint, essentially all they'll be seeing is they'll write some code. After some time, they'll then get an immediate review of exactly what they've written and if there have been any new problems generated from either the code that they've written or the code that uses the code that they've written. And from that, they're then able to make decisions to either rectify those problems immediately or get additional information about each problem. And then from that, we're able to refine our model based off of whether or not they're accepting these changes or if they don't accept our changes verbatim, but instead make other alterations to ensure code consistency. We can also learn from those as well. And this cycles back into our overall process. So we're able to then learn from how users are interacting with each change that we've recommended to them, as well as how that change subsequently affects the same code base. Because when that change gets committed or that PR gets reviewed, we're then able to learn was there anything that we might have missed from our recommendations that we can then add in the subsequent review stage? So let's go over a couple of general examples. They'll span a couple of different use cases that we've had. And again, these are all sort of available on our VS Code extension. And as a comparison point, we can use a very standard approach where you basically just ask Copilot or ChatGPT or any LLM model that you might use. If you just feed it in code and ask, is there any problems here? We'll compare it for that as a baseline. So essentially here, we're able to detect race conditions or other runtime problems, and that's something that sets us apart from more of the static rule-based tools, that why they are very specific in what they can detect. There's quite a few things that they can't detect because they rely on runtime information or other best practices that may not be easily encoded into a simple rule. So from there, we're able to determine that within a certain function, based off of how they're interoperating with other components in runtime, because we're able to extract information about what that runtime environment might be like, either from the docs or the packages that are being used, or the other libraries that may be called, exactly which areas are potentially dangerous, either due to a lack of internal consistency or poor state management. We can also detect logical inefficiencies or other excess code complexity. So areas where the efficiency of the code could be improved based off of a structural understanding of how each component calls every other component within the code base, and whether or not certain branches may include excess calls or unnecessary calls that are not easily something that you would be able to embed within a bit simple setup. And in instances like this, raw LLMs can also struggle to find these sorts of problems simply due to the lack of specific understanding about what the call chain might look like in a particular sample, which is something that we embed directly.
You only have 3 minutes.
Okay. Compared to Sonar or other Copilot tools, we have very specific examples or specific use cases that are more runtime focused, which is something that is only really capturable if you're looking at either the logs from production or have a very senior developed staff or comprehensive tests. And even in those cases, there's always room for error. So we can provide another set of eyes, essentially, to preemptively detect these while you're doing the development process and really offboard a lot of the extra load of making these decisions within there. And it's especially important for generating complex applications, using AI for generating the code directly, simply due to the fact that it's difficult for the AI to be consistent across multiple files, which is something that we can provide some additional correctness checking for. We only have a couple minutes left, and I do want to go through a short demo of our VS Code extension. So I will go through these next couple of slides pretty quickly. This is another set of algorithmic inefficiencies, as well as some other logic problems relating to a particular automotive use case that we have been used for. Essentially, this is also related to inefficiencies within memory usage of these protocol buffers that they were sending data to as part of their system for doing OTA updates. In addition here, there's some broader design problems that we can detect. These are more architectural in terms of how things are structured or how modular individual pieces of the code base are. We can give some additional information about how to either make it more clear or also make it more usable or maintainable in the future. So clicking next here. Perfect.
You want to talk about it?
Yeah, so essentially, this is our VS Code extension. Feel free to try it out on your own code bases if you have any open source projects. Essentially, what we'll do is while you're writing code, we can provide up-to-the-minute feedback based off of what problems you may be generating or any potential detections that you might have. You can then ask some additional information or just get an immediate fix and directly apply it to the code base itself.
Well, as the demo finished to load, that's pretty much all from us. Again, we're Metabob. If you guys want to test out the tool, you can find us on VS Code, GitHub, Bitbucket. So love to hear your feedback. It's free, the tool, for any developers. If you work for a company that is interested in our on-prem solution, you can reach us out at metabob.com. Just, you can book a demo there. Always happy to get developers' feedback at any time. So it's been a pleasure being here. Thank you all, and looking forward to your questions. Thank you so much, guys.